Hello, my name is Aaron Balke, and in today's video I'm going to be breaking down my K-Nearest Neighbors classification modeling assessment for my Masters of Data Analytics. This assessment uses a theoretical hospital dataset in order to do the analysis, and this presentation will have some assessment-specific information in it. Just be aware of that as you are watching the presentation. I hope you enjoy. Hello, my name is Aaron Balke, and today I'm going to be breaking down my D209 Task 1 Classification Analysis Performance Assessment. This is revision number 1. I didn't get the first video assessed yet, but I figured with the problems I did have earlier just to re-record the video. So whoever assessed it, the previous parts was very hard, so I figure I should just get this out of the way and re-record it, all that good stuff. So, but today's classification analysis, and we're going to be using K-Nearest Neighbor classification in order to answer our research question, which is which conditions and patient demographics are correlated with high blood pressure patients. And this is following the same research I've been doing for my D208 for my logistic and linear regression models, where I'm trying to figure out what's related to high blood pressure and how we're able to correlate and generalize patients around high blood pressure, because high blood pressure is an all-cause. It leads to stress on the heart, which is all-cause mortality. From the CDC, we were able to see that 26% of the United States deaths right now are coming from heart disease and stuff related to cardiovascular complications. And so if we're able to figure out what's related to high blood pressure, we would be able to help our own hospital system. So that's the research question and the mindset behind it. The goal of this analysis is to create an accurate and effective KNN classification model. The hope is to make one more accurate than my previous research, my previous models. So the logistic regression model got an 80% accuracy, and so the hope is to make a KNN classification model that has a higher accuracy than that. And justification-wise, the way a KNN nearest neighbor model works is that when you get a new data point with an unknown label, you try to look at the points surrounding that with a K amount of points around that new data point and examine those, see what the labels are on those, and the most frequent label on those surrounding points is what you apply to that the new data point. That's the predicted label. So that's how a KNN classification model works. The main assumption of KNN is that if points are close to each other, they must be related. And so that's a very simple and powerful way of modeling these classifications. However, it's very sensitive to the inclusion of insignificant features, and it's a massive assumption that if these things are close together, then they must be related. We are going to be using Python version 3.10.9. We're using Python because it's a straightforward language, has strong data analysis support, and has a ton of library and package modules in order to help with data science. It automates a lot of the hard work of data science. We're using Jupyter Notebook as our environment, version 6.5.2, and we're running Jupyter Notebook because of the checkpoint functionality. The checkpoint functionality allows us to have access to the state of a model, the results and the state of the model after running it, if we close down the program or if we do other stuff before that block of code, and also we don't have to keep rerunning the model over and over again to get the state that we already ran once for. So that's the power of Jupyter Notebooks. We're going to be using pandas because pandas provides the data frame object, which allows easy manipulation of large data sets. We're going to be using NumPy. NumPy is very helpful for quick computing of standard deviations, the absolute values, minimum, maximum of a bunch of numbers. So NumPy is very handy for that. We're also going to have Seaborn and Matplotlib. Those are going to be included because they help with visualizing data. So it'll make it much easier to validate and do the reporting of our model. And then finally, for the big one we're going to be using is sklearn. And sklearn is going to be used, it provides a ton of stuff. We have the standard scaler for scaling our continuous variables. We're going to have the training test split in order to help evaluate the model. We're going to have actual metrics to evaluate the model. I believe it's the AUC curve we're going to have in here. And then we have the KNN model object itself for the analysis. We got the grid search CV, which allows us to automate hyperparameter choosing. So we'll be able to test KNN model using a bunch of different parameters to find the best one. And then we will also use select kbest for feature selection. So those are our packages and libraries. The major goal of the pre-processing is going to scale the continuous independent variables. They have to be scaled in order to avoid high magnitude variables, something like income that can go all the way up to 100, 200,000. We don't want that affecting the distance-based analysis that KNN classification is. And so we want to scale all those continuous variables to be the same size and between 0 and 1 in our case in order to not skew the data. Here is all the chosen variables. It's a few numeric and a few categorical ones. So got all of those here. When it comes to the preparation of the data, we need to, we're going to do some standard stuff like check for duplicates, check for null values, and remove unused features. We're going to do that to make it easier to do the analysis and to make it more efficient. If we have too many ones that too many variables can become a problem after a while. So then we're going to convert the in the data frame, they're called object data types, and we're going to convert those into categorical variables. And then we're going to create dummy variables from those categorical variables, and that allows us to take the categorical variables and turn it into a bunch of Boolean. So like if you have gender, for example, which is male, female, and non-binary, you split that into a male feature, a female feature, and a non-binary feature with zeros and ones. And so you convert the categorical into Boolean features, which is required because the model needs numerical data. We can't shove a string into it and hope something works. So that's what's happening there. And then, converting the Boolean data. The Boolean features are in the data frame right now as yeses and nos, and we're going to want those as zeros and ones. And then finally, we will scale the continuous variables, and we want to scale the continuous variables in order to prepare it for the KNN classifications. We mentioned the requirement to scale the data earlier. So let me run all of these. Okay, should be running now. Yes, it's going through it. Okay. So we got all the standard imports up here, and then we have those individual sklearn package, I guess sub packages that I mentioned previously. So each one of those are in here as well. And then we import the data from the CSV. We check for duplicates. If there are any duplicate records, that would show up as a number here in the first value of this set, the shape set, and we get 0, which means we have 0 records that are duplicated. We do a similar sort of thing when it comes to missingness, when it comes to null values. If there was any sort of records with null values, it would have a value here, which there's not, 0 records. So we have no duplicated data and no missing data. Next step is to drop all the columns we don't need. So I removed a bunch of the location-based stuff and a bunch of the survey data. So just took those all out here. We then have the categorical data that we take it from an object type into a categorical type in the data frame. We then have all these Boolean values, which we convert from yeses and nos into zeros and ones, 1 for yes, 0 for no. And then we have the numerical features here, and we'll need that for the scaling, so have those here. And then we convert the categorical variables we do have into those dummy features, the individual features for each categorical value. So you have in gender, as we mentioned, you have a male column now, a female column now, and a non-binary column. We do make a variable of all of the feature names for easier use in the future. And then we do scale the continuous features between 0 and 1. Originally, I did use a manual taking the minimum from the current value and then dividing that by the standard deviation. I did do that originally, but the assessment said I had to use a package in order to do the scaling, so I did just replace that with min-max scaler. It should be the same exact scaling, the same exact outcome, where it's just a scale between 0 and 1. I'm not sure why that wasn't okay, but I hope this now works. So we just do that on all of the continuous variables, which are in the variable numeric variable. All the continuous variables are in the var numeric variable, which we're able to fit and transform using the scaler. Then we have the export dataset here. This was another thing that had to be I got marked down on. I had them separated, the X and Y variables, the independent and dependent variables. So now I have them as one here. I think that was the only other problem. It also wanted, the assessment wanted me to have the splits done previously. I may have misunderstood that, but the splits are here, and it does export as CSVs, all of that good stuff. So that's what we got here going on. We got the high blood pressure, which is going to be our dependent variable. We make a new data frame of just that value, and then we drop that from the independent variables, and then we got a independent variable data frame as well. And then we do that splitting of the training and test sets. I'm using a 20% test split because that's the standard. It's I usually go between 20 and 25% depending on how many records we have. So that's what we got going on here. We export it all as CSV files. I'm trying to see if there was anything else worth mentioning. I guess for this revision, the one main thing that I did make a mistake on previously was I did run multi-collinearity and p-value backwards elimination on the variables we did have, but since it's a distance-based analysis, it is not important to do that. And so I removed those functions from this analysis. Since it's distance-based, we don't need to worry about, because it'll just grab the things it's closest to, and if it's not important, it'll be it'll be gone. So don't have that anymore. But onto the actual analysis. So in order to perform the KNN classification, there are two main steps. So the first one is to choose the correct number of KNN, the number of neighbors. And so we run multiple KNN models using different values for K, different numbers of nearest neighbors. And after running many of those through the grid search CV, we're able to find the one with the highest score, and the one with the highest score we use for creating our optimal model that we actually run everything through finally. So we're going to be using grid search CV to automate this process, and the way grid search CV works is it uses k-fold cross-validation. So in our situation, it takes our training data and then splits it into 5 sections, 5 even sections, and then names one of those the test section and trains the model on those other 4, and then scores it using that test one. And then it does that again with a different one of those 5 as the test section, and then scores the model using the other 4 as training. And it does that 5 times, one for each. Each bit of data is used as a test set once for each set of hyperparameters, and then it creates an average score of those, and then that is the score of that set of hyperparameters. And so we run that. In our situation, we're running that 10 times. I have a range here of the hyperparameters we want. So we want to test for 1 through 10 nearest neighbors, how many, the value of k will be between 1 and 10 for our automated process for checking the best and optimal number of nearest neighbors. And so that's what we got going on here, and after running it, we got back that the best parameter for nearest neighbors is 2, and the best score was 56%. So that's the first step for our KNN analysis, and so now we have the optimal number of k neighbors. And so now we will create a new object, a new KNN object that has those best parameters, and then we fit the training data to it and then make a prediction using the test data. So when we do that, we get back the Y prediction data, and we compare that to the Y test data to see, using a confusion matrix, how close we got to being accurate. And when we do that, we get back that our accuracy was only 56%. And so from looking at the confusion matrix here, we can see that we did get a lot of predictions correct. That we said that a patient did not have high blood pressure, and it was true that they did not have high blood pressure in 985 of the 2,000 times that we had that value there. The problem occurred when it came to choosing saying that they did have high blood pressure when they did. We were not very good about this. We said that they didn't have high blood pressure far too often when compared to the actual data. And that's why our accuracy is seen at 56%. It's a little misleading because it says 56%, so that sounds like we at least got half of them right, but it pretty much was us just saying, yeah, they got high blood pressure or don't have high blood pressure every single time, which is not a useful model to have. If every single time it just says, yeah, they don't got high blood pressure, just saying that constantly is not effective. So and we can really see that by using our area under the curve visualization. The area under the curve, the worst possible area under the curve visualization is a straight line from the bottom left corner to the top right corner. A best case scenario would be to have a vertical line up to the top left corner and then a horizontal line all the way to the right. So this, where our score was a 50.1%, almost a 50.2%, which means we are 0.2% more effective than randomly guessing. So our model was very ineffective at splitting the patients with high blood pressure from the patients without. And so those distributions, it's having a hard time seeing the split between those two. It can't really observe and distinguish the two groups effectively. So unfortunately, the model was not very good at doing that, and we had only ever tried saying that they had high blood pressure at 339 out of the 2,000 records, and so it was not guessing that patients had high blood pressure pretty much ever, the results and implications. Our hope was to have a model with an accuracy of 80% or more to do better than our logistic regression model that we did previously. And this was not it. It could not do better than our logistic regression model. It is not good at making predictions with the data we do have. The limitations of this model, there are a lot of categorical or binary variables that would probably make more sense as continuous variables, particularly when it comes to distance analysis. The use of categorical and binary variables removes a lot of nuance when it comes to data. And so, for example, the overweight feature. There's a large difference between someone who's a little overweight and someone who's morbidly obese. And so putting them in the same group, in the same category for the overweight feature removes a lot of nuance when it comes to that variable specifically. And so for me personally, I would think when it comes to the distance analysis, it would be better to have a continuous variable like BMI, where you're able to have a much larger range with more nuance in it in order to make more effective distance analysis. So that's one major limitation with this data set, and that would actually be my recommendation, is to get more continuous variables instead of using binary variables for this sort of analysis. And my final recommendation is not to use this KNN classification model for finding links between high blood pressure and other continuous variables. It would just be better to use the logistic regression model we used previously. That was far more effective than this, and I wouldn't even call this remotely effective. Of a 0.1, 0.2% effectiveness, greater than randomly guessing. So I would not recommend using this at all, and either use the logistic regression model or move on to another type of analysis in the future. So that is my recommendation. That is my D209 Task 1. This is the revision version, so I hope you enjoyed, and have a good one.